Un, deux, un, deux. OK. Donc, merci tout le monde. Thanks everyone for coming to this session. Today we're going to talk about how we can get better GPU access on the web with WebGPU. Yes. So during these 40 minutes, I'd like to go through what kind of a context of what GPUs and WebGL are and how WebGPU improves on that, along with a bunch of demos, and hopefully you'll be able to learn at least one thing during the presentation. That's my goal today. So for the last 3 years, I've been working on WebGPU and leading the effort to implement the standard in Chromium, which is the open source browser that's also used, for example, for the next version of Edge. And also, I've been co-chair of the WebGPU W3C community group since it was created in 2017. And fun fact, I grew up here in Toulouse, or close to Toulouse. This is a tiny town called Pechabou. I know there's some people coming from there. So, WebGPU, what is it? It's the successor to WebGL for GPU access on the web. Great, that doesn't really help. So first we'll look at what GPUs are, just kind of a quick recap to make sure everyone's on the page. So if you look at the GPU, well, let's start with contrasting with a CPU. So a CPU usually has a bunch of cores, and each of the cores are optimized to do a stream of serial instructions in the most efficient way, to make them run as fast as possible. And so that influences the design of CPUs in many different ways. For example, if we open a CPU core, what we see inside is first a very large control unit. This is the part of the CPU that selects the instruction to execute. And it does a lot of things to try to be faster in the serial stream of instructions. It does branch prediction, reordering, register renaming, speculative execution was a fun one recently. So there's this large control unit, and there's a reasonably small arithmetic and logic unit that actually does the computation. This is kind of a small part of the CPU, and it goes along with the registers. Another interesting aspect of CPUs is that the memory accesses are also optimized for serial execution. So the memory is optimized for low latency instead of bandwidth. There still is reasonable bandwidth up to, say, like 100 gigabytes. Let's contrast that with GPUs. So GPUs are designed to run parallel workloads very, very efficiently. In a GPU, there's a number of blocks, kind of like CPU cores. But in each of the blocks, there are many, many different arithmetic and logic units, along with their registers, but just one control unit. So what happens is that the control unit chooses one instruction, and all the ALUs are going to execute the instruction on different data because they have different data in their registers. So this is just more efficient to run parallel workloads because you just have more transistors dedicated to doing the actual computation. If we look at the memory access, it's also optimized for parallel computation because it has much higher bandwidth but lower latency. And this is fine because GPUs do some kind of hyper-threading, but on steroids, to hide memory latency when you're running parallel workloads. And finally, there's also in GPUs a fixed function unit to do, say, triangle rasterization. That's useful for games, but it's a kind of a small part of GPUs. So this is what GPUs are. Now the other part of this was, hey, what's WebGL? So as a quick recap, WebGL is a JavaScript API that allows, it's a JavaScript API inside web browsers that allows JavaScript to access the GPU through WebGL, which is kind of similar to the OpenGL family of APIs in native. So that's what people were using on phones until recently. So WebGL allows you to do games on the web, great. But I'd like to showcase some other applications, types of applications you can make with WebGL. So this first one here is some cool scientific visualization. This is a map of the brain. I think this one is a fly. And so you can explore the brain in 3D and see how, like, as you take different slices, how the brain structure evolves. And this is really important for scientists to figure out things about the brain of flies. But what's really cool here is that previously, this type of application, you had to install like whatever software on your Windows box, and like all of a sudden MSVCRT 71 DLL is not there, and like it would be really hard. But with a web browser and WebGL, people are able to put their data, and it's accessible to everyone instantly, super easily. It just works. So this is a big power of WebGL. Another way to use WebGL outside of games is to do geo-visualization. And I think the best example here is Google Maps or Google Earth, this one. So, I mean, everyone knows it. You can just like go around and see things. This one is the WebAssembly version of Google Maps that's in beta, and it's using WebGL for its rendering. And finally, WebGL can also be used to add effects to your application, to your more regular web page, instead of doing a huge application that's centered around WebGL. So for example, this one is, I'm not actually sure what it is, but it's some kind of scrolly telling about corn. But the point here is that the web page is augmented with WebGL, so it gives this amazing look with it. I don't know, it's just pretty. Anyway, it's very fancy, and it looks nice, and it keeps people engaged. So that's good. All right, so that was WebGL. And now we're going to talk about WebGPU for the rest of this talk. So WebGPU, it's also a JavaScript API, and it's being standardized at the W3C, where a lot of the JavaScript APIs are being standardized. And what's important here is that WebGPU is a group effort with all the browser vendors involved. So we have people from Firefox, from Safari, from Edge, from Chrome, obviously. But we also have a number of users or like hardware vendors. For example, Intel is heavily involved. So what's great is that it's really a group effort. And when WebGPU is finished, we know it will be ubiquitous. And so you'll be able to use it everywhere. And WebGPU, of course, the goal is to improve on WebGL. The question is, how does it improve over WebGL? And we're going to go through each of these three. Well, actually, not how it maps better to the hardware, because it's less interesting. And also I had some other subject I wanted to talk about. So WebGPU and WebAssembly and how you can use it to make stuff, for example, like the WebGL Google Earth demo we saw before. So better CPU performance. If you look at JavaScript 3D frameworks, they usually structure a scene in what we call a scene graph. And like the name implies, this is a tree data structure where you put objects and subjects in this hierarchy. So for example, we do a racing game. We're going to have a car that the player drives, the road you drive on, and a nice background, for example, a forest. What's interesting here is that in this structure, we can really see the decomposition in sub-objects. And if you want to change something about the car, you can say, hey, the car is now in this other place. But automatically, because of the structure of the scene graph, the body and the wheels of the car and the doors are all going to be moved at that same position as well. So you could say, hey, everything could be inside the car. And so if you move the car, it's just one object and you move it. But the wheels and the doors, they work independently of the body of the car. It would be weird if the body of the car was rolling like this. So because they are animated differently, they're sub-objects. In a scene graph, usually we call all of these nodes. And a simple scene graph implementation in WebGL could look like this. So every frame, the game logic and the request animation frame takes the root node and says, draw yourself. And recursively, we're going to draw the whole scene graph. So the first thing the node does is it computes its own transformation in the world, its own position and orientation in the world, given the orientation of its parent node. This is how we do the car that has wheel as sub-objects. Once it has the transform, it will just draw everything itself and its children with that transform. When doing the actual commands, WebGL commands to do draw, it looks like this. So first in WebGL, we set up the 3D pipeline. So we set up options like how triangles are rasterized, how our colors are blended together, how the different vertices of the mesh are fetched from memory, etc. And then we give a bunch of resources to WebGL to do the drawing. For example, textures, or more textures, or like transformation matrices, things like this. In WebGL, both of these are a lot of commands, like maybe 10, 20, 30 more. And there's a lot of work being put in WebGL frameworks to optimize the number of commands that are done. This is like the most important thing they can do. But it's not the most interesting, and also they still have to do a lot of these commands every time. And so once we have done these setup steps, the only thing that's left to do is just draw the car. Well, this is a lot of commands, and one of the big elements of design of the modern GPU APIs, so WebGPU is, let's say, is modern for today, one element of design is to try and factor all the cost upfront while you load your application or your game. This way, while you're running the game, you have really amazing performance, and loading time is less important. So this is one element of design. And the second one is that it tries to see the GPU as a bunch of functions that operate on data versus previous APIs that see the GPU as some kind of state machine that you modify things on. So let's look at how we can factor costs at loading time. In WebGPU, you can factor things by creating the state of the pipeline at loading time. So instead of doing setup 3D pipeline in WebGL, you just create one object that's called the pipeline object. And then when you need to use it, you just set pipeline. But that's one call. Likewise, for resources, when you load your scene, you have a model, you load the resources for the model, and you create a group of resources. We call it bind group. And then you can just say, hey, use this group of resources. That's one call. And then when you're done setting up things, you just call draw to, like before, to draw the car. Okay. Another way to, so like this is great because we kind of reduce maybe 10x the number of commands in the best case, but it doesn't give the huge improvements that we hope from graphics APIs. So let's go back to the racing game example. So we're racing in the game, and it looks like this. And turns out I'm a really bad driver, and I crash in one of the trees. So as you know, the platane, they don't care about cars crashing into them. So the platane itself doesn't change. There's no rendering change. However, on the other side, the car, well, it's completely wrecked. So the rendering needs to change. And we can see that how in a game or a graphics application, there are going to be parts of the scene that change and parts of the scene that do not, like the background. So we can classify nodes as dynamic and static. Here, the world is dynamic because the car is dynamic, because its components can change in reaction to things like crashing in a tree. However, the background just is always going to be the same. So one core design of modern GPU APIs is to also allow the reuse of GPU commands. So the same way we were creating pipeline and resource group objects while we were loading the application, we can create bundles of commands that we can replay instantly later during the gameplay. So in this case, in the constructor, if the object is static, we can pre-compute all the GPU commands. And to do this, we need to create a bundle of render commands. And the way in WebGPU we create the things with commands in them is through an encoder, because it encodes commands in memory. So here we have this render bundle encoder. So it's the thing that creates render bundles. And we just say, hey, all subtree, put your GPU commands in this bundle. And then when everyone has done that, we just get the list of bundled commands. So this is at loading time, so it's cheap in a sense. at draw time, when we detect we are the root of a static subtree, we, instead of like walking all the children and sending all the commands, we can just reuse the bundled commands in one call. And so this is much more efficient because it allows you to just remove the computation for a whole subtree at once. So since we started having a prototype of WebGPU in Chrome, we partnered with Babylon.js. It's a 3D framework in JavaScript that's fairly popular. And we made a demo with them of this and the gains we could have. However, the demo broke in the last 2 weeks because this is still super experimental. So that's the bad news. The good news is I have a YouTube video of the demo. So, so this is what I will show right now. So on the left, yes, on the left, this left for you. On the left, this is WebGL. So this is going to be the WebGL version of the demo. And on the right is the WebGPU version of the demo. So what we can see is when we start, the two on both sides, performance is roughly the same. However, as we start getting up and seeing more of the forest at once, WebGL gets slower and slower. That's because it has to send commands for each and every object individually. On the other side, WebGPU is much faster because there's only few commands to do with just like draw all the trees independently, but still, it's just one command with the bundles that we saw. So this is kind of a synthetic benchmark that really showcases the feature, but this is the type of gain we can hope to have for large backgrounds in applications. All right, so that was how WebGPU allows getting better CPU performance than WebGL, because you can just pre-compute a lot of things and do more with fewer calls. This is especially important because currently in JavaScript, you're mostly on one thread. And so if the WebGL commands take a lot of time, then you have much less time to do the actual work and the logic of your application. So WebGPU will allow you to do more in the logic of your application. Another big benefit of WebGPU is that it gives you access to what we call GPU compute functionality. So GPUs, as we saw before, they're great at parallel processing. The reason for this is that if you were making a video game, which is what GPUs were originally designed for, if you make a video game, you're going to draw a lot of pixels every frame, and each of these pixels will run roughly the same computation, just on different data, because the pixel is at a different position on the screen. So for example, this is a screenshot from a demo from Babylon.js, and this is a very, very tiny part of the code that's run for each of these pixels. I don't know if you can read it, but there's a lot of math, and there's a lot of memory accesses also in that code. So each of these pixels is going to execute, I don't know, thousands of instructions each frame. So because of this, GPUs evolved to become more and more efficient at parallel processing, where the instruction is the same, but the data is different. Each pixel does the same thing, just on a different position. And so around 2008, GPUs started being used for scientific computing. I think that was around the time NVIDIA came out with CUDA. And so then the scientific community started using it for, I don't know, fluid simulation, things like this. But turns out there's a class of scientific computing that's really interesting these days. It's machine learning. And GPUs are really, really good at training machine learning models. So this is the really fashionable side of GPUs today. But anyways, so GPUs became very good at parallel processing. And WebGPU allows you to use that in a very flexible manner with what we call compute shaders. So we'll just walk through Compute Shader 101, which is doing a matrix multiplication in a compute shader. And it's kind of a simple way to do matrix multiplication. But we'll see later that it can have amazing gains compared to doing the computation on the CPU. So I won't go through matrix multiplication, but the point here is that for each of these, each of the cell in the C matrix, we are going to have to do a bunch of computation, but for each cell, the computations are similar. So in a way, we could see each of the cell as the pixels on an image that we are rendering. So this is what we're going to do. We're going to execute the same program on all the elements of the matrix with different data very efficiently using the GPU. And this is what we're going to go through, and whatever, there's a drawing, so you don't have to read the text. Basically, what we need to do is execute something on the GPU. So that's the program thing in the red box. To do this, we need our matrix data on the GPU. The reason I say this is because the memory spaces for CPU and GPU can be separated. Sometimes they aren't, but sometimes they are. So we have to assume they are separated. So the first step is going to be to take the input matrices and put them in GPU memory. So A and B go from CPU memory to GPU memory. Then we execute the program on these two matrices to produce C on GPU memory. And then we bring the results back on the CPU so we can do useful things with them. I mean, for matrix multiplication, you probably want to keep it on GPU because it's a lot of data, whatever you want to do with it. So the first step is to initialize WebGPU. And this is the simplest part. You just create an adapter. An adapter is a view of a GPU in your system, but you can't do anything with it. It's just to query information about it, so you can be like, hey, which extension do you support? How many ALUs do you have? Things like that. And once you're happy with the adapter, you create a device. And the device is kind of the root object of a WebGPU application. Then we create the memory allocations used for the matrix. So in WebGPU memory allocations, we call them buffers. And here we say, please create me a memory allocation that is mirrored by a CPU allocation. Well, a GPU memory allocation mirrored by a CPU memory allocation that has this size in bytes. And I'm going to use it for a storage is the name for, I'm going to use this with compute shaders. So we get these two allocations, we put data in matrix A, and then we unmap. And this is a bad name to say, please do a copy from the CPU side to the GPU side. The reason the name is named like this, the thing is named like this, is because when the memory spaces are the same, we can actually get something like mmap in Linux. And so we get faster performance. So we unmap the memory, and then we do the same with the matrix B. And for C, we create just the storage on the GPU, not on the CPU, because we don't have anything to put in there. We're just going to get the data back. Then we create the resource groups, like we saw before. That's called the bind groups. It's kind of a detail of how the API works. It's not really useful for compute. It's more useful if you're making a video game that has to do a lot of commands every frame. Let's just assume we have to put the different buffers in a group so we can use them with the program. Then we need to write the GPU program that is going to do the matrix multiplication. So this example here is using GLSL. But there's like different programming language that could be used, and the WebGPU standard has not yet settled on exactly which shading language it should use. So here, for this example, I'm going to use GLSL. This is the declaration of the interface of the program. So it says which resources the program is going to use. And in this case, we see we have our three matrices. Then this is the actual program. So this main function is going to run for each cell of the C matrix. What we can see here is the GL global invocation ID, which is basically the coordinate of the cell inside that matrix. This is the first piece of data that is different between the ALUs on the GPU, and so this is what makes the SIMD processing start. I won't go through through the detail of this algorithm. I mean, it's not that interesting nor hard, but so we do the computation, we sum things together, and we store it in the resulting index. So here, we just computed one cell in this program. Finally, this was the GPU program. It's a string, but you need to put it in assembly form or ingest it on the GPU, so there's a compilation step somewhere. This is the compilation step, the way it's done in WebGPU. Now we have everything ready to do the computations, but we still need to send the commands to actually do the thing. So to do this, we create a command encoder, like we saw before. Encoder is just like a builder object for GPU commands. Then we start a compute pass, set the program, set the resources, run the program. Here we say run the program. Please do it on all the cells of the C matrix by saying run on 124 by 124. So here we have computed the value of the matrix C on the GPU, but we also need to bring this data back on the CPU. So to do this, we create a readback buffer, so a CPU memory allocation that can be copied to using the GPU. And in the commands, we also add a copy from C on the GPU to C on the CPU. So great, we have everything, except we have just created objects. We haven't asked the GPU to do things yet. So this is the last step, where we just get the built list of commands, and we say, hey, GPU, do this. So this is the submit call here. It just says, please now do these commands. So as you can see in WebGPU, there's a lot of setup just to build up to the submit command. But everything we've done before is necessary. Finally, when we submit the commands, it's an asynchronous process because GPUs are asynchronous coprocessors, and the computations can take a long time. So to read back the data, we have to use an async function. And this gives us an array buffer object. So with this, we've done the hello compute, it's called, which is basically the simplest matrix multiplication possible on GPU. So I have small demos of this. The first one, OK, let's start with this one. So this is a tiny application. There's going to be a link to it later down in the slide deck. But it's the version of the demo that works on Safari with the shading language that Safari supports. So here, let's say I want to compute a multiplication of a 512 by 512 matrix. GPU took 0.01 seconds to do it. And the CPU is still going. Come on, do it. Anyways, GPUs are much faster if you want to do these things. OK, and we also see that the computations matched. So it means the GPU didn't cheat. It actually did the computations. There's the same thing in Chrome. It happens to be faster on the CPU. I don't know why. Probably, I mean, whatever. But anyways, the GPU is still super fast, and the CPU is still slow comparatively. So that's why you want to use GPUs for this type of application. All right. So that was how WebGPU gives you access to GPU compute, which can unlock more things, like scientific computing and machine learning on the web. The final thing I wanted to talk about, and it's not really an advantage of WebGPU per se, because WebGL can still be used with WebAssembly. But one big advantage of WebGL is that you can take your, say, Android game that uses OpenGL and compile it, and it works on the web. WebGPU doesn't have a native API like this, so it's hard to see how a native applications could target the web the same way using WebGPU. So to understand how we are going to be able to do this, we'll see how WebGPU is implemented in Chrome briefly. All right, so this is a very, very basic view of how Chromium works. So on the left side, you have the render process. It's the process in which the tabs live. And on the right side, there is what we call the GPU process. For security and stability reasons, we put the GPU process, the GPU driver, in a different process, just so things work better and are more secure. But anyways, if you're a JavaScript application and you use WebGPU, what's going to happen is first, on the render process side, the WebGPU commands are going to flow to something we call dawn wire, which is an IPC, like inter-process communication serialization thing, that will send the command through serialization, deserialization to the GPU process. So the WebGPU commands are forwarded to something that we call dawn native that lives in the GPU process. And this thing is the library that implements WebGPU on top of many different GPU APIs depending on the system. So it supports D3, D12 for Windows 10, it supports Metal for all the Apple platforms, Vulkan for Linux, Android, Chrome OS. There's also some experimental OpenGL support. Anyways, dawn native is a library that we're interested in. So now imagine you're an application and you want to be able to use WebGPU in native. Well, you can just remove most of Chrome and put your application right on top of dawn native. So doing this, your application is portable, but also can target the web easily. Because what happens next is that when you put your application in WebAssembly, all these dawn native calls that are used are going to be translated to WebGPU JavaScript calls. And the reason we can do this is because the API of dawn native is the one-to-one equivalent of the JavaScript API. And actually, dawn native is not the only library you could do this with. Mozilla has their own library written in Rust called WGPU native that exposes the same interface as dawn native, so you could build on top of that as well. So this is what JavaScript code looks like versus the C++ code for the same API. It's mostly the same thing, but with type annotations. So you can see how the translation to WebGPU in JavaScript would be trivial. And yes, so WebGPU is fairly new, and we didn't really have any WebAssembly support until now because it's a lot of toolchain work. But with coworkers, we've kind of worked a lot over the last couple of weeks to make this happen. And the demo worked on the train here yesterday, so it might not exactly work. We'll see. First, this is what we call the aquarium. It's a benchmark in WebGL. And the open source team at Intel ported the WebGL benchmark in native. So we could benchmark web versus native, web versus different APIs in native, etc. So it takes a while to load, but it's nice looking aquarium with lots of fish, which is the benchmark part, because the benchmark is how many fish can you draw. Now, the same source code from just a different make directory we built with mscriptn, and hopefully it works. It takes a while. But anyways, the idea is that you have this tool chain. Yes, you have this tool chain, and you build your application for the web, and just works, essentially. If you want to learn more about WebAssembly, Steve Klapnik has a talk about it in, I don't know, this afternoon, I think. But the point here is that WebAssembly is great because it's a web technology that also has huge benefits in other parts, and that's going to be Steve Klapnik's talk. But WebGPU also is a web API that's made to be portable because it's the web. It has to work everywhere. But it also has uses in native where if you want to have a portable graphics API that's good enough and also allows you porting on the web, and that's the important part. All right, so we've seen all the advantages of WebGPU. It has better CPU performance. It gives you these compute shaders that can do scientific computations in a very nice way and efficient way. And we now have WebAssembly support for WebGPU so that you can build something in native and just like put it to the web, and it works. So as a recap, WebGPU is the successor to WebGL, and it's made by all the major browser vendors at W3C. So we have people from Firefox, Edge, Safari, Intel, all these fine people in the group making an amazing API. Everything you might want to know is on webgpu.io. You can take a picture or just remember it. It's fairly easy. The link to the compute demos is on there, but the aquarium is, I mean, it worked yesterday, so maybe it will appear on this page in a week or two, just the time we clean it up and we make it more robust. But it will be on there eventually. With that, thank you. And do we have time for? OK, we have time for one question or maybe two, and then afterwards I'll be at the office hours downstairs. So let's take the first question. No questions? OK, you, sir.
I have a question regarding how does this API maps with like more bare metal APIs like Vulkan, and because like I'm a contributor for an open source game engine, and we don't have to we don't want to have a middleware between like the Vulkan one and the web export one. So we wanted to implement both, like a web version and a Vulkan one. So how do like both API maps, and would it be easy to
OK, so
version without like a lot of rework?
So WebGPU is what we call an explicit API. So it's very similar in concept to the modern desktop APIs like Vulkan, Metal, and D3, D12. You could see it as Vulkan Lite. So it abstracts some of the hardest things from Vulkan, like memory barriers, memory allocation, the fact that you have to adapt to the hardware geometry with different types of queues, etc. So one way to see it is you could use WebGPU and it gives you Vulkan for, but it's an easier to use API and portable. The other way to see it is today there are translation layers from almost all API to all other APIs. So we haven't studied that yet, but there will eventually be something that takes Vulkan and maps it to, like, translates it to WebGPU in a good enough way. But nobody has looked at that just yet. All right. Well, thank you, everyone. I'll be at the office hours, and see you there.